I become a little too shy for love? I've been hurt before. All's fair in love and war. So I'll snuggle up close to the shell I'm living in. And if I let you in, another round begins. No, I'm spinning in a vicious cycle. I'm scared of doing something I'll regret. Maybe this is right, but I'm still staring at your silhouette. What if you're everything I need? A fire in my heart, the air I breathe. What if I'm incomplete without you by my side? What if I go against my heart instead of confessing from the start? What if I miss out on the life meant for us? I need you by my side.
Should I be scared? The feeling's so different now. You got me floating here, a feather in the air. Oh, but when the wind blows, will I tumble or sail away? Or would you have me stay? And what if I escape? I know
I'm spinning in a vicious cycle. I'm scared of doing something I'll regret. Maybe this is right, but I'm still staring at your silhouette. What if you're everything I need? A fire in my heart, the air I breathe. What if I'm incomplete without you by my side? What if I go against my heart instead of confessing from the start?
Please take your seats. Our program will begin in 5 minutes.
I need you by my side, by your side. I'm not afraid. We found something that'll never fade. We can be ourselves and figure out the rest along the way. What if you're everything I need? A fire in my heart, the air I breathe. What if I'm incomplete without you by my side? What if I go against my heart instead of confessing from the start? What if I miss out on the life meant for us? I need you by my side. I need you by my side. I need you by my side.
Please take your seats. Our program is about to begin. Please take your seats. Our program is about to begin.
Good afternoon, everyone. Please take your seats and welcome to this plenary session, afternoon session. This is the first time in FCRC's history that we're having a plenary panel session. And for this, we are grateful for the Computing Research Association, CRA, hosting this panel. As you know, CRA was one of the founding participants of organizing FCRC 30 years ago in 1993, and we're grateful for the CRA also hosting this panel in celebration of CRA's 50th anniversary. With this, I'd like to hand the podium over to Dilma Da Silva, the plenary speakers chair.
So hi everyone, it's my pleasure to introduce you to the facilitator for the panel. Mary Howe is a professor and director of the Collard School of Computing at the University of Utah. Since 2015, she has been a member of the CRA Board of Directors, and from 2009 to 2013, she chaired the ACM History Committee. Her research focuses on programming system support for high-performance computing. She's an IEEE Fellow and ACM Distinguished Scientist. Thanks, I'll pass to you, Mary.
Thanks, Dilma. In 1972, a group of North American department chairs in the emerging field of computer science got together and formed the Computer Science Board. The goal of the Computer Science Board was to provide a forum for discussing issues and sharing best practices. And from the very beginning, CSB's membership was 75% from academia and 25% from industry, recognizing the importance of this kind of academic industry collaboration. So the CSB was the precursor to CRA, so what CRA became. And in 1973, this group helped to organize the first computer science conference, which was in Columbus, Ohio. And it was both a research conference for the whole field and also a place for people to find jobs and interview, start the interview process. So I don't think it's too much of a stretch to say that that conference, which then became an annual ACM conference and went into the 90s, was a precursor to FCRC, or is a close approximation to it. So I also wanted to point out that several of the conferences here at this year's FCRC were formed roughly about the same time frame. So Stock is a little bit older, and ISCA, as you know, is celebrating its 50th anniversary, and PLDI and POTSI aren't very far behind. So this is a 50-year retrospective, and this panel is going to reflect on lessons from the rich past of our field. And we're not just going to think about what was important, but we're also going to talk about why. So this includes the surrounding technological, economic, and social considerations of the time that led to some of the research that was prioritized during this period. And so this kind of retrospective, I know we have a lot of students in the audience, this kind of retrospective is really important to you because it allows you to look at some of the decisions that were made in the past and why they were made, and it helps you to think about where to go in the future. So this is coming, I don't have to tell you all, this is coming at a time when computing has permeated every aspect of our everyday lives, and it's also a time, looking across the research here at FCRC where machine learning is really reshaping how we solve problems in our field. So without further ado, I'll introduce the panel, but let me first say what the format is going to be. So I'm going to introduce all the panelists, and then they're going to each give brief opening statements, and then we'll have a series of questions that from me. Towards the end, we'll open the questions to the audience, and then we'll end with closing statements, and it's going to be pretty quick, so let me get started. Our first panelist is Hagit Attiya, and by the way, they're sitting in the order that I'm going to introduce them. So our first panelist is Hagit Attiya. She's a professor at the Taub Department of Computer Science at the Technion Israel Institute of Technology, and she holds the Harry W. Labov and Charlotte Ullman Labov Academic Chair. In 2015 to 2019, she was the Technion's Executive Vice President for Academic Affairs. Her research deals with fault-tolerant distributed computing, and she co-authored a core book in this area. She won the 2011 Dijkstra Award in Distributed Computing for the first asynchronous fault-tolerant simulation of shared memory in a message passing system. She's editor-in-chief of Springer's Distributed Computing Journal and a fellow of the ACM. Our next panelist is 2021 Turing Award laureate Jack Dongarra, recognized for his pioneering contributions to numerical algorithms and software that have driven decades of extraordinary progress in computing performance and applications. Dongarra also specializes in the use of advanced computer architectures, programming methodology, and tools for parallel computers. He holds appointments at the University of Manchester, Oak Ridge National Laboratory, and the University of Tennessee, where he founded the Innovative Computing Laboratory. In 2019, he received the ACM-SciEM Computational Science and Engineering Prize. In 2020, he received the IEEE Computer Society Computer Pioneer Award. He's a fellow of the AAAS, ACM, IEEE, and SciEM, a foreign member of the British Royal Society, and a member of the US National Academy of Science and the National Academy of Engineering. Okay, and to my left, the next panelist is Lizy Kurian. She's a Truchard Foundation Chair in Engineering at the University of Texas at Austin. Her research interests include workload characterization, performance evaluation, memory systems, reconfigurable architectures, and high-performance architectures for emerging workloads. She has teaching awards, she received the Penn State University Outstanding Engineering Alumnus, and she has research and teaching awards as well at UT Austin. She's co-authored books on digital systems design using VHDL and Verilog, and edited a book on computer performance evaluation and benchmarking. She's currently editor-in-chief of IEEE Micro and holds 16 US patents. She's an ACM and IEEE fellow and a fellow of the National Academy of Inventors. Huan Liu is a Regents Professor and an Ira A. Fulton Professor of Computer Science and Engineering at Arizona State University. He received the ACM SIG KDD 2022 Innovation Award for outstanding contributions to the foundation, principles, and applications of social media mining and feature selection for data mining. At ASU, he's been recognized for excellence in teaching and research. He co-authored the textbook Social Media Mining and Introduction. He's editor-in-chief of ACM Transactions on Intelligent Systems and Technology, and founding field chief editor of Frontiers in Big Data and co-founder of the International Conference Series on Social Computing, Behavioral Cultural Modeling, and Prediction. He's a fellow of ACM, AAAI, AAAS, and IEEE. And our last panelist is Guy Steele, who's had longstanding impact on the programming language community. In 1971, he joined ACM and implemented a Lisp interpreter for the IBM 1130. Since then, he has been involved in the design, documentation, implementation, maintenance, or standardization of the following languages. And I'll prepare you, it's a long list, and I'm not going to list all of them. Mac Lisp, Scheme, Tech, S1 Lisp, Spice Lisp, Common Lisp, C, Star Lisp, C Star, Fortran 90, HPF, Java, JavaScript, and Fortress. He's worked on substantial projects in APL, Fortran, COBOL, RPG, Focal, BASIC, ECL, Pascal, Haskell, C++, Python, Perl, Excel, Scala, Coq, and BibTeX. And he's also well-versed in Algol, Snowball, Bliss, PL1, Clue, Prolog, Smalltalk, Modula 2, Ada, Standard ML, OCaml, Icon, and Clojure, among others. His history credentials include co-chairing the 4th ACM SIGPlan conference on the history of programming languages in 2021. He's an ACM, IEEE, and AAAS fellow and a member of the US National Academy of Engineering. And so now we're ready for opening statements, and we'll start with Hagit.
So actually, I want to go back even to before ACM was established, and note that many years before that, researchers, scientists like von Neumann and Turing started studying computing as a phenomenon that is intrinsic and is not connected to actual devices that do computation. And in doing so, they established foundations that understand that transcend the specifics and the here and now of how things are developed. And I consider this to be one of the reasons computer science has been so successful, because by doing so, we could study the computing without being tied to specific implementations. And we could see this, the impact, the way it impacted, at least in two ways. One is from an engineering perspective, allowing to develop and improve specific components and devices independent of each other in a way that they still mesh together, and we capitalize on improvements done separately. And from the usability aspect, it meant that that users, programmers, and algorithms, for example, could work with abstract interfaces that again remain the same regardless of how they're implemented. This has been a blessing. I think this is one of the most important reasons computer science has succeeded so much in such a short time. But also, in a sense, it's also been a detractor, because many people that see these simple, nice interfaces that computer science provided to computers, for computers, and they don't really appreciate what goes underneath it. So people don't really appreciate what it means to press the message, write a message to your friend, and it's showing up in their phone in like milliseconds. So I think we should be exploring how this great success of computer science have brought us here, and what it will allow us to do in the future.
Great. Jack?
So let's see, I'm a computational scientist, I guess. I started my career 50 years ago at Argonne National Laboratory. At Argonne, we had a supercomputer, and it measured performance in terms of megaflops. Fast forward to today, we have machines which are 12 orders of magnitude faster than that, running at exaflop performance levels. And getting to that point, we had roughly a 3 orders of magnitude improvement in performance roughly every 10 years. Every 10 years, there was an inflection point in terms of the hardware that gave a boost to the performance. And that's been going on for a number of decades. In the last few decades, things have slowed down. And the slowdown was probably the result of Dennard scaling ending, as well as slowing down of Moore's law. Going forward, when we look at what we could expect in terms of performance levels, the projection would be that we would only get one order of magnitude in about 8 years. So something has to change in terms of how we put together our scientific computers. Today, our large-scale supercomputers are really put together based on Intel parts, x86 architecture, together with commodity interconnects with accelerators thrown in. And that combination leads to perhaps a high peak performance, but the realized performance of these computers is really quite less. And we should probably take some lessons from our hyperscaler colleagues and think about designing hardware that better suits the problems that we have to solve. What we have with hyperscalers, they're going out and designing their own hardware to solve their problems. And that extends even to car manufacturers, like Tesla designing their own chips. So in the future, I think we're going to have to make some more fundamental changes to the way the architectures are put together.
Lizy?
Computing has changed our lives phenomenally in the 5 decades. Think of 1973. The microprocessor was 2 years old. Some of you may remember the panels we had 2 years ago in ISCA at microprocessor at 50, and some of you contributed to the special issues as well. So now 2023, the microprocessor is beating. It is 1,000 times faster in clock speeds, 1 million times larger in number of transistors it contains. And not just those, how it is enabling a lot of applications to change our lives. I would just think of the pandemic, and life continued relatively at whatever pace it could move on. School still had classes, exams still happen, all because of the state of the art of computing. And I think we all should be proud of what happened. But as I think of the changes during these decades, I am remembering a story when I was a graduate student in the 90s in the computer lab. I was sitting, some new student comes in, he goes and sits on a computer and he types in, what is 2 plus 3? And it gives him an error, it doesn't do anything. So he's like, this computer doesn't know to add? I just asked what is 2 plus 3, it doesn't know it. And everybody nearby, they are laughing, looking at him. And after a while, someone told him, hey, you need to write a program, you need to compile it, and you need to run it. And he is, I have to run something? It doesn't know 2 plus 3? That looked ridiculous at that time. But today, I can ask Alexa, what is 2 plus 3? I can ask many more questions. It would answer it. So the big change that has really happened is many things have become more end-to-end. Our applications, our programs have become more end-to-end. But with that end-to-end transition, there is a lot of inefficiency that has crept into the process too. When someone added 2 plus 3 at that time, maybe there were 10 instructions, a dozen instructions, or something like that. Alexa would be taking 1 million instructions to do or more to do the 2 plus 3. And so when you think about the layers of software and layers of things that are happening in a computer system and the inefficiency that is there, it's actually pretty big and full of overhead. We are doing things very luxuriously. Our models, the ML models, of course, are huge. If we are going to use computers to help us with even the most mundane tasks every day on a routine basis, how sustainable is that going to be? We may want to think about that. Programming in those days was meant to be efficient for the hardware. We all took a lot of pride in writing the most bare metal, most optimized assembly language code to do something a bunch of decades ago. Now, efficiency, I'll put a statement out and Guy can comment later on it. I would say programming languages nowadays are tuned towards the efficiency for the human, productivity for the human. In those days, maybe we didn't have enough transistors and gates, and so everything was tuned for efficient use of the computer, whereas now it's all about productivity for the human. I think, humans have become the scarce resource, and transistors and gates have become the abundant resource. So there are a lot of problems to think about, but I'll stop there.
Great. Juan?
Yeah, I think the student you met should have used the Lisp. Huh? Okay, so I will talk about 2 points about AI. Okay, one is about AI is evolving. The second one is an existential risk of AI. Okay, so I remember when I was a graduate student, we chanted, knowledge is power. So we thought like if we just encode enough knowledge into rules, the intelligence would emerge. But then, of course, you think that the things change, right? These are very fragile rules, easy to break. And some people say, hey, why don't we just learn from the data? And give me data, I will learn rules for you. These are the decision tree induction algorithms. But then backpropagation, I don't know if you still remember, revived the connectionist approach, okay? And then we started, of course, there were like 2 approaches, symbolic and connectionist, but a symbolic won, okay? And it's a long story, but I won't tell you this. And then backpropagation algorithms revived the connectionist approach. Then we have the deep learning, right, came up. Then people say, hey, if we have enough computing power, if we have data, we probably will also have the intelligence, okay? So, is this true, right? So AI, the pursuit of AI continues. But now let me move on to the second point of the existential risks. Okay, how many of you haven't used ChatGPT? You haven't. Okay, so not many people haven't, okay? So the recent large language model technologies is freaking many of us out, right? So, and other hypes about these GPT a mirage, right? But it's anybody's guess. And however, it does raise the awareness and associated risks with these technology. But for me, a clear and present risk is actually the misinformation, okay? The misinformation. And there are letters circulating for signatures and many speculations, right? So, but a misinformation, from my point of view, is something we have to deal with immediately. Okay, we have deep fake, we have voice cloning, we have well-written messages, right? These intimate dialogues and human-like chatbots make you like easily, believe that you are talking to some super intelligence, okay? So the problem is, it's a game changer. It is not that easy to detect this misinformation just like a few months ago, okay? So why? Because first, the more human-like these chatbots are, the better they are fooling at people. They are at fooling people. Second, humans are often gullible and irrational. So we are very easily manipulated, okay? So this is the third is disinformation, fake news with large language models. They travel faster and deeper. So we face these immediate danger. Okay, this immediate danger. This morning, right, the keynote talked about the trust. NSF, they talked about the middle one is about the trust. It is really, really important piece of work. So now we are forced to change our ways of consuming information and interacting with people. So I think as AI researchers, we need to develop novel tools to tame misinformation. That's all.
Thank you. Guy?
Thank you. 50 years ago, there's a tendency to try to design the one best programming language for all purposes. Since then, we've come to accept that it's good to have different programming languages for different purposes. In the 1970s, there was a big debate about control structures. This actually occurred at ACM 72 and throughout that decade. It's mostly settled down now. If, then, else, and while do are now universally accepted, but it was not always so. Some languages have a form of case or switch, and several widely used languages get along without the goto statement. But Dijkstra's guarded commands, for example, have been abandoned. And likewise, data structures have become relatively standardized. Integers, floats, strings, arrays, some sort of record structure, and linked lists and trees are well understood. Major topics still being debated today include type systems, whether to enforce types at compile time or runtime or both, how best to specify abstract or parameterized types, whether to avoid or to embrace side effects and how to constrain them. What is the best mix of imperative, declarative, functional, object-oriented, and logic programming styles? Java, 25 or more years ago, started as a mix of imperative and object-oriented, but since then it's become much more functional and stream-oriented in style. And recent designs such as Clojure and Verse continue to explore novel mixtures and trade-offs of styles. Over the last 50 years, the enterprise of language design is increasingly informed by ever more complex mathematical theories. Examples are denotational semantics, abstract algebra such as group theory and lattice theory, type theory, category theory including functors, morphisms, and monads, higher order logic. But I think the most successful efforts to use theory to guide language design have not let too much of it leak through to the programmers. You shouldn't have to think too much about category theory just to add up an array of numbers. Sometimes programmers must be very concerned about efficiency, and different languages provide different ways to manage efficiency. In the 80s and 90s, there was a lot of debate about whether garbage collectors could ever be efficient enough as efficient as a programmer-managed memory allocation. But nowadays, much improved GC techniques are used in many languages, but perhaps not for the fastest supercomputer applications. There are places and times to do programmer-managed memory allocation or to use some other strategy. Rust, for example, uses an alternative storage management technique based on a novel type system, and that's interesting. Another example is that the original design of C, and C still, allows programmers to declare which variable should be stored in CPU registers. But very quickly, compilers got so good that they were doing better than programmers, and so programmers have largely abandoned that particular feature. One question I ask myself about any new language: what can you know about a program without actually running it? Will it terminate? Is it guaranteed never to crash? Will it actually compute what we want it to compute? What can be said about its execution time? And will that program maintain data privacy? Different languages provide different answers to these questions, in part because tools to answer those questions have gotten better and better over the last 50 years, and in part because language designers, even today, may judge that programmers will accept new limits on expressiveness in exchange for new safety guarantees or other advantages. Programming language design always involves decisions about what to make it easy for the programmer to say, what the programmer can say but with difficulty, and what the programmer cannot say at all. Programming languages bridge the gap between what a programmer wants to say about a computational task and what a hardware architecture can actually do. And both of these are constantly changing, and that's why I think there will always be a place for the design of new languages and their adoption.
Great. Okay. So now we're ready to ask the panelists some questions. And in honor of ISCA's 50th anniversary, the first question is going to Lizy. So looking over this 50-year history of ISCA and computer architecture research, what are two most striking observations you would like to make about the evolution?
Okay. Looking at the papers from the last 5 decades and the research that was happening, one thing I would say is academic research that's not, it's not very clear at the time that it is happening, where it goes, or will it be used, or is it relevant? Maybe it might take a few decades before it becomes really useful, or it is evident that it is useful. I'll pick an example. Systolic arrays were something that was happening in the late 70s and 80s. And not everybody thought it is all that useful, and they had their own conference conference on systolic arrays. It took some papers, the Watt papers, but looking at all the ML accelerators and architectures coming out now, every one of them, including the Google TPUs, they are all use systolic arrays. It might have taken 3 decades for it to show it's useful. Another one perhaps might have been interconnection networks, and has become much more useful, or it's more clear that they are useful a few decades later. That's one observation. Another one I would say is approximate ways of evaluation and analytical modeling has become a little bit more popular now compared to maybe the 3 decades in between. Early on, the first and second decades of ISCA, probably the circuits, the chips, the architectures being talked were smaller, evaluation was pretty rudimentary, but Mark Hill is sitting in front of me. So I guess late 80s, 1990 onwards, there was no paper accepted in ISCA for maybe 25 years, which didn't have trace-driven simulation. In 5 years, it changed to execution-driven simulation, cycle-accurate simulation, cycle-by-cycle simulation of things. But now, in the last maybe 5 or a little more than that, you can see papers which are, because you can't handle cycle-accurate simulation for the kinds of things we are doing now. So some evaluation models have, which were not favored, have become a little bit more favored now. Roofline analysis is being, the same. Some of those who favor trace-driven and execution-driven simulation are favoring analysis like roofline analysis now. So I would say, basically it is sometimes some of those things that are not clear or not favorable, things will go and come back.
Great, thank you. Next question is to Jack. In the nearly 50 years since the introduction of the Cray 1 in 1975, high performance computing has seen many changes, as you talked about in your opening statement. And I'm interested in how architectures and software have evolved in relation to not only technology, but also the applications that we are running.
Right, so I mentioned these inflection points that happen roughly every 10 years when the architecture really changes. Going from scalar machines to vector machines caused an upheaval in some sense with the applications to invest in terms of vector processing. The next inflection point was perhaps shared memory architectures that entered the scene. The attack of the killer micros is the thing that took over after those vector processors. Again, an upheaval in terms of the applications. And then came message passing, where we went to a distributed memory architecture. Again, a major change, an upheaval in terms of the applications, having to rewrite those applications to fit the architectures. And today, we're in the era where we have accelerators that augment that message passing paradigm. So many changes taking place, a lot of architecture giving rise to applications, giving rise to implementations that have to be performed to match, in some sense, those architectures. We really need a better way of describing what the needs are and doing what, there's a code word we have called co-design. And that co-design is intended to get the architects together with the application people, together with the software people, to design a system that would actually fit the needs of what was going on. But the reality is we don't have co-design. We basically design a machine to fit some rough parameters, what's the cost and what's the peak performance, and that architecture is assembled and thrown over the fence at the application peoples who now scramble for the next 5 years to try to get their applications to fit within that framework in some sense. And that causes a lot of churning, where I think if we went back and did a true code design where the application people got together with the hardware, got together with the software people, we might be in a better position.
Great. And Guy, is there a tension? This is kind of a follow-on to what Lizy said in her opening statement and what Jack just said. Is there a tension between what hardware designers can build and what programmers want to be able to say, and how's this changing?
Yeah, there are a couple of three tensions I could talk about. I can think of at least a couple. One is just the issue of parallelism. The hardware evolution that Jack just outlined involved ever increasing amounts of array processing and parallelism and distributed processing and so forth. And parallelism just seems to be hard for people to manage. My experience of consciousness is that I pay attention to things in a somewhat sequential order, and that's kind of the way I organize my thoughts. And we have developed techniques for managing parallelism. I mean, there's a lot of stuff going on in the world, not just in computers. And right now I'm not paying attention to San Francisco or Tokyo, although I'm very interested in those cities, for example. But we learn to pay attention to things. We use techniques of aggregation and abstraction and delegation to do these things. We've learned to organize things in hierarchies, for example, not just in computer science, but in mathematics and in other parts of science. And that leads me to my second point, besides the tension between the desire for sequential thinking and the architectural use of parallelism to get better performance. There's just the fact that, quantum computing aside, all the computers we build, if they're operating properly, are effectively all finite state machines. And we know a lot mathematically about finite state machines. And we don't like thinking in those terms, I think. When we deal with things in a hierarchical fashion, we're dealing with recursive tree structures, and we seem to prefer to organize our thinking about computational tasks in terms of languages that are bigger than the bottom of the Chomskyan hierarchy. We like to think in hierarchies and then deal separately with the fact that the depth of those hierarchies may be limited by resource constraints. So those two tensions then introduce tensions in how we design software and how we design languages that bridge that gap from software to hardware.
Thank you. Next question is for Hagit. What are examples of theoretical contributions to computing research that foreshadowed contemporaneous directions in the field?
So one of them, I'll give two examples, one from the more general theory area and the other from my own area of distributed computing. So from the more general area, I would say it's the study of randomness. Which I think is a very key part of theory of computing research. Its impact on cryptography, RSA, complexity-based cryptography, zero knowledge, etc., is well documented, and the usage of these tools is well known. But even more, I think with the big news of the day, the generative language models, it's known actually from probably the early 90s that in some sense machine learning is about predicting especially generative AI is about creating the next token, in a sense, based on an existing token. And in a sense, this is generating sequences that are very non-random. Which could be seen as a kind of an inverse of what pseudo-randomness is about, which is creating sequences that look random as they are generated. And I think this research that, again, goes back to the 90s, I think is starting to do a comeback in order to understand generative AI as an inverse of pseudo-randomness. Going to my own area of research, I would probably point out the consensus problem, probably the bread and butter of distributed computing, presented at the very late 70s, early 80s, as a problem about spacecraft control, and then morphing into problems in database management. It went out of fashion for a long time. It was well studied in the 80s when I started my academic career, but then it became an obsolete topic, like nobody does this. And somehow, surprisingly, in 15 years ago or so, it was resurrected in the form of Bitcoin and then generally in blockchain. Blockchains went out of fashion a little bit in the last 2 or 3 years. They were the ChatGPT of 2 or 3 years ago. Still, it was interesting to see a problem studied in one way, resurfacing in another way, and adapted to different applications. And the similarities and differences were quite interesting for me. And I think I want to use these 2 examples as, again, to go back to something that I said before, is the importance of identifying key problems that try to go to the essence of what we are doing, and then still being agile in the way we apply them to the world around us and to the problems that come our way.
Great, thank you. Next question is for Huan. AI is in the news and not for the first time. And you talked somewhat in your opening statement about how things have changed over the history of the last 50 years. And I wondered if you could expand on that a little bit and maybe talk about some of the solutions that we might have learned from the past.
Okay, yeah, I'm glad to. So I have this opportunity to talk about AI again. So the short answer is the goal remains the same. Okay, the methodologies change. If you can remember, like from knowledge is power to data is the new oil. Okay, I think in 1956, when the AI was born, and people tried the goal was to build machine intelligence. But what is intelligence? It's difficult philosophers are arguing about it, right? So then people are intelligent, humans are intelligent. Why don't we just mimic humans? So there are 2 approaches. One is about mind, and it's more about like how do we solve the problem? That's a symbolic approach, okay? Then the second one is about brain, then McCulloch-Pitts, and they published a paper in 1943, talked about this artificial neuron, so there's a connectionist approach. But then people also, I just mentioned about the symbolic and connectionist, and Marvin Minsky and Seymour Papert, the Perceptron's book, and killed a connectionist approach. But then that's why when I was a student, we just learned expert systems, Mason's, E-Mason's, implemented in Lisp. I read his book, actually, when I was a student. And it's about Lisp. But then, as you know, these rules are very easy to break, and there are so many exceptions. And then people try to use like the decision tree method to like a card and ID3, but then backpropagation. Then AlexNet in 2012 really started this new deep learning movement, okay? So this is sort of the methodology change, but the goal remains the same. However, the question remains, can we really achieve artificial general intelligence? So I think I will stop here.
Okay. And this next question is to Guy. You also have early experience with AI and AI programming, and how have the programming systems for AI changed during this time?
Oh yes, they've changed tremendously. At the beginning of my career, when I was at MIT and hanging around MIT before that, in the 60s and 70s, a lot of the approaches to AI were, let's invent a programming language that will allow us to then write the robot, you know, the artificial intelligence thinking program. And just off the top of my head, efforts at MIT included Comet and Meteor, which were token processing languages largely aimed at linguistics, and Planner and Conniver, and the scheme language that I invented with Gerald Sussman was actually an attempt to make sense of Planner and Conniver. And these were theorem-proving languages. The idea was that if only we could solve logic and theorem-proving, then we could build the thinking robot. And there are other efforts at Stanford University, in addition to the SAIL language called LEAP, if I recall correctly, wanted to represent symbolic triples and make that accessible through an algo-like language. There was an effort at, I believe, the University of Rochester for a language called Telos, which was an attempt to make a language for teleology, starting from Pascal and adding on symbolic processing capabilities. So in the 60s and 70s, there was a lot of emphasis on symbolic processing and particularly symbolic processing for logic in an attempt to capture intelligence. And then those gave way in the 70s and 80s into so-called knowledge representation languages, which were less about describing computational processes and more just about representing the information that an intelligent program would need to know. And perhaps the pinnacle of those was Doug Lennett's Psych project, CYC, which is essentially an attempt to encode all of Hewlett-Packard knowledge in a symbolic form, which once assembled then would be presumably fairly easy to search and find the answers to questions that your artificially intelligent thing would want to do. What happened in the last 10 or 15 years? There was a side thing called neural networks that got explored in the 60s, and neural networks effectively got killed for a long time by the book called Perceptrons, written by Minsky and Papert, where they showed that a particular limited kind of neural network had computational limitations that appeared to be insurmountable. And that kind of discouraged the investigation of neural nets, but it made a comeback. And I won't recount the entire history of neural networks to you right now. That has led the delayed investigation of neural networks led to the deep learning models that we are using now. And those proved to be quite fruitful and quite effective. The only problem is that I don't understand what they're doing, and that worries me. Because they involve large amounts of numerical computation which produce results which look interesting and possibly trustworthy, but I really don't understand how all the numerical crunching underneath got us there. I'm hoping in the future for a synthesis or perhaps a resurgence of symbolic explanations of the numerical processing that went on underneath. Nowadays, we're seeing deep learning producing sequences of tokens that perhaps can then be further symbolically processed. There's an interesting paper at PLDI this week on neurosymbolic computing. So that may be where the future is going as these two threads converge again.
Thank you. This question's for Hagit. With all the recent dramatic changes to computing, can we still research and teach computer science using a layered approach, heavily relying on abstraction?
So it's a hard question. And it's tempting to say no, really, because you've heard in the discussion here that co-design and so on and so forth, that architecture cannot be ignorant of programming languages, and languages cannot be ignorant of AI, and so on and so forth. Still, I really believe this has been one of the secret weapons of computer science. And I guess the answer is probably we can go at our own ways, but we cannot be ignorant of what the other topic areas are doing for research, and same for teaching. And I've been listening to Guy talking about how neural networks became effective when basically computing power became so powerful that just what seemed like an insurmountable complexity deficiency became not so important. I was listening earlier to the stock panel discussing P versus NP, with the feeling that if something is an NP, it's not computable. And then if you go to PLDI, you'll see that people talk about set solvers. Set solvers, this is solving NP-complete problems. Okay, and if it's not doubly exponential, they are not they don't wink at all. So I think we can go, each of us, in our own research areas, but we should be very aware, and again, this should be reflected also in our teaching. What's happening in other areas might change the way we think about what we are doing. And again, I think this is a good point to give a plug for FCRC, which gives us an opportunity to hear each other.
Great. And this question is for Jack. What will future architectures, software languages, applications, and other things look like?
Wow, okay. Let's see if I can answer that. Well, I don't have a good answer for that, but I think we need more research in terms of hardware. I can remember a time when there were many hardware projects at universities exploring the space and coming up with innovative ideas on how to make things work. Those ideas, of course, have had an impact, but I think we need more investment in terms of getting to the fundamental issues of architecture. and trying to understand how the hardware can be put together. And experiments need to be done at scale. So we need to build machines which have a reasonably good mix of complications so that those ideas can really be tested and understood at some level. You know, our dirty little secret today in the scientific area is that most of our applications get less than 5% of the theoretical peak performance out of the architectures that we have. And I think we can do a better job with that. And that'll, again, coming back to the point of doing some co-design, working with hardware, the people designing the applications, people designing the software, the languages, getting together to make that mix a little bit better.
So I'm about to ask the last question of the prepared questions, and we're going to take a few, we're tight on time, but we're going to take a few questions from the audience. So there are 3 microphones, and I'm going to ask, first ask Lizy the last question. What do you think will be the biggest challenge for computing looking forward?
I think the biggest challenge is going to be sustainability. And we heard about yesterday's keynote, foundational models, what all wonderful things they can do for us. And if we start using those foundational models or such large models for most everything we do, probably, is it going to be sustainable? I'm not sure. But actually, we are coming up with fancy architectures, fancy models, fancy applications, and everyone is fascinated. And the world is really liking everything. There is enough economic activity coming from that as well. So how are we going to decide how we address the sustainability? Another important thing I think that bothers me is the architectures have become, or systems have become so complicated that no one can really understand everything that's happening. Till a few years ago, we could teach students everything that happens in a computer. That's not possible anymore. So if we are designing these complex systems, will we be able to analyze and understand them and optimize them and improve them? So are we going to have enough observability and enough hooks to know what's happening? Is anyone going to be able to understand the layers of software and the large complex architectures we are going to have? There is one more thing that really worries me, which is if we have all these foundational models that can help us in a lot of things. In the light of that, what do we believe are still foundational things that humans need to know, and what are we going to teach our 5-year-old to maybe 12-year, in that middle school period or elementary school? We threw away spelling, we threw away cursive handwriting, what all are we going to throw away and what are we going to keep? It's one thing when we know to read and write, we can look at what ChatGPT produces and says, yeah, that's good or that's bad. If you don't know to read, so will we throw away reading and writing? So maybe there is something larger to think about. How are we going to take this forward? That worries me.
Great. So we'll take a question over here.
Hi there. Thank you for your time. Thank you for sharing your insights. We're reflecting on 50 years of computing, and I've been alive for only half of that time. So I'm wondering if you have any either anecdotes or warnings of things that we shouldn't forget or things that we should learn right now to prepare for the future.
Juan, do you want to take that question?
Yeah. Okay. From my point of view, young people just do it, right? But okay. Yeah, in order not to repeat the mistakes, yes, of course, you need to learn. And I think with computer science, we have these historians, they write these things. And so by reading books will help. However, if you talk to an old person, for example, they have too many lessons to give you, then you won't be able to be audacious and to do anything. So that's the trade-off. You have to do it. Like I remember, it's try fast and fail fast, right? That's the motto. I think in this age of information, unfortunately, if you try to read the history too much, then you will fall behind. I understand you have to read a lot of histories. I do, but I'm old, you see, so that's...
Yeah, go ahead.
If I could add to that, if you go and talk to an old person and he or she says, we tried that 25 years ago and it didn't work, don't take that for an answer. Ask, why didn't it work and what's different today?
Yeah.
It's all different here in the context.
Let's take a question over here.
Hi, this is Dave Patterson from Berkeley and Google. I just wanted to comment on Jack. You know, at the hyperscalers, because of the focus on machine learning, they're doing code design, right? It's not so much taught in law. And every year since I've been at Google, I've wondered how significant is machine learning, and it seems like every year it's got more significant, and it seems like it's last year it's made a giant jump. So I think the question kind of for me is how much is machine learning is going to eat of software? There's been fields within close to AI where they've just thrown all the algorithms out because the deep learning was better, and they really needed new textbooks. Does the panel think this is going to, is this a wave that's sweeping over all of computer science, or it's like, well, now we were talking about blockchains a few years ago, we'll be talking about something else in a few years?
Do you want to answer?
Well, I think it's more like fire than CB radios. So I'd say that this is something that's real. It's impacting all areas. It's certainly impacting computational science, and going forward, I think it's going to be having more of an impact. It's not going to replace physics-based modeling. It's going to augment that. It's going to complement it. And I think it's going to really revolutionize how we approach many problems. So again, this is an inflection point in some sense caused by the way in which we approach problems. I have to say that in the scientific area, we're envious of the hyperscaler guys. You guys have the money and you can invest in designing your own chips. In the computational science area, we don't have that luxury of having that great resource that would allow us to build our chips that meet the needs of our applications, and we're forced into using commodity parts. So I'm very envious of the hyperscalers and the things that are going on at Google and other companies.
Thanks. Thank you. Question over here.
Hi. Thank you for the wonderful insights over this entire panel. I'm TB Shardle at MIT CSEL. So co-design has come up a couple of times during this panel, and one concern I have is whether whether there's too much overfitting happening in this co-design process, or the co-design process that's being envisioned. Too much overfitting that we're doing between the languages and the architectures based on the codes that we have today, without enough forward thinking of the codes we may have tomorrow. Is that a concern that any of you have? And if so, how do you imagine addressing it?
Who wants to answer?
I think several of us refer to it in a sense, and we should just be careful and aware of what we are doing and not overfitting, and still, taking a step back and doing our own things in a more abstract way.
Good. And this should be the last question. We'll take a question over here. Last question from the audience.
Sure. Ben Zorn from Microsoft Research. I'm following up on Dave's question on AI. So we've seen incredible progress with this notion of the high-level language and the target architecture, and trying to figure out how to translate down in the co-design over the last 50 years. So I have a provocative question. So should we rethink the relationship between the high level and the low level? The high level being humans, but the low level now being LLMs. So instead of thinking about targeting hardware, our current well-specified hardware, we think about the target architecture now is the large language model, because they're so much more capable than our current hardware architectures. And would that be a productive direction for the field?
Maybe Huan.
I can try, but
and then maybe
you can talk. Okay, so I think you put too much bet on the large language models. Okay, so I think, for example, the large language models The best one now, they are trained on the data by September 2021. So anything happened after that, it's not there. Okay, so, but also now it seems like the intelligence is just about to predict the next word. Like I just increase the number of tokens from 10,000 to 5,000 to whatever thousand number of tokens, the intelligence will emerge. So the other work will be like, how can I just do the efficient optimization so that I can squeeze as much as computation into it. But I think we should try other methods. No, we should not put too much bet on large language models. And there are many reasons, but we can talk offline. So I let the guy talk about it.
I just hope that the large language models will graduate from predicting the next word to predicting the next sentence or predicting the next paragraph. And maybe what they write will be a little more coherent.
Okay, so thank you all for your great questions from the audience. And then I have one last question for the speakers. So we're going to do this in rapid fire. So what advice do you have for the students in the audience in selecting research problems that will stand up to the test of time? And start with Hagit.
Yeah, I don't know why did I have a name that starts with an A, but anyway. So I would suggest not to be afraid of artificial intelligence, to meet artificial intelligence with our human intelligence, creativity, and values for a brighter future.
Here's what I tell my students. Find a problem that you're passionate about, something you really care about and you really want to work on, that you are passionate about that. You should aim high. Don't go for the low-hanging fruit always. You should aim high in terms of difficulty. You should expect to fail. It's a research area. Don't expect to hit a home run every time. Failure is part of the process. And the final thing is to maybe network, talk to other people, express your ideas, and don't be afraid of somebody stealing your ideas. Talk to them and bounce ideas off each other. You can have tremendous collaborations as a result of that.
Great. Lizy?
Architects are in between technology and workloads. There is the push and the pull. Technology makes new things possible. And so to students, I would say, watch technology, watch workloads. And that'll give you plenty of opportunities to contribute. There are lots of things to fill this more architectures to fill this universe and the metaverses that are coming. And when you are doing that, simple is elegant. Do things, do not make them any more complicated than what they need to be.
Yeah, and when you pursue your interest, that's very important. And just try to make unique contributions. Don't follow the crowd. Okay, so just do something different. Make your contribution.
And my advice is similar to what everyone else has said, especially Jack. Keep the big picture in mind. Look for opportunities to bridge disciplines rather than rat-holing on just one. Don't settle for just 5% improvements, aim big. And finally, read voraciously. Read papers, read code, read books, absorb as much information as you can. You never can tell what you learned 5 years ago might suddenly be relevant now.
Okay, with that, I want to thank our panelists. Please join me in thanking our panelists. Oh, I don't count myself as a panelist. I wasn't clapping for myself, just so you know. And I want to thank the audience, and I definitely want to thank Dilma. Actually, let me just give some credit for Dilma she did an enormous amount of work in organizing this panel. Yes. And thank you to ACM and to CRA. And with that, we'll adjourn. Thank you.